السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. In the name of Allah subhanahu wa ta'ala, I would like to start this very wonderful and special session of this afternoon. First, I would like to welcome our dean, Dr. Abdul Majid, of the College of Engineering. I would like also to welcome the department chairs of College of Engineering, Dr. Ghaffar and Dr. Yasser. My very dear and valued colleagues and faculty members, welcome to this session. And the most special guests are our students and young kids. Welcome. Thank you very much for coming to this very, inshallah, interesting session. Our guest today is a very remarkable person. Okay, he is specialized in a field of my interest, so that's why I'm standing here, starting this session. Thanks for giving me this opportunity and allowing me to be here welcoming all of you. Our guest, I'm just going to tease you about him. He's a very special person that is actually role to get sometimes impersonated in movies, in Hollywood movies. Yeah. So if you see, I will not say the name of the movie, it will be recognized later after the session or as soon as the session is started. Okay, so please take every chance and take this opportunity, pay attention to the talk and prepare some interesting questions to excite our presenter to give us some of his special expertise and knowledge. Before I welcome our guest to the stage, I would like to welcome Dr. Rovers to come to the stage and present the speaker and give you a short bio about him. Thank you.
Assalamu alaikum wa rahmatullah jami'an. It's a great honor and a pleasure for me to introduce to you our special guest today, Professor Charles Ilashi. Professor Charles Ilashi is a professor of electrical engineering and planetary science at the California Institute of Technology. He was the director of the Jet Propulsion Laboratory and vice president of California Institute of Technology. He oversaw the development and operations of over 45 flight missions and instruments. He has been a principal investigator on a number of NASA-sponsored studies and flight projects, including the Shuttle Imaging Radar series. So he was the science team leader. He's the Magellan Imaging Radar team member. Also, he was involved in the Cassini Titan radar as a team leader and a co-investigator on the Europa sounding radar. He is the author of over 230 publications in the fields of active microwave, remote sensing, and electromagnetic theory. And he holds several patents in those fields. Professor Charles, on behalf of PSU, I would like to welcome you here again. The stage is yours.
Shukran was salamu alaikum. So you can tell a little bit from my accent that I'm originally from the Middle East. I'm originally Lebanese. And I want to thank you for hosting me here today. This is a great pleasure. This is my first visit to your university. So hopefully, but I come fairly often to Riyadh because we have a joint program with King Abdulaziz City of Science and Technology, which I'll mention a little bit. So what I'm going to talk to you today is to kind of give you an idea about the latest development which are happening in both space and Earth exploration. I cannot cover everything in 1 hour, so I'll be picking a few examples to illustrate. But one thing particularly I do when I go and talk at universities is to show particularly the young people that I see many of them sitting in here, the excitement of being an explorer. Because each one of you is an explorer. As you are studying, you are learning new things, you are exploring new things, you are advancing things if you are doing research or even taking classes. So you should consider yourself as an explorer in addition to being a student. So I want to show you a little bit the fun of being that, because that's what I spent all my life. I was like you, and I ended moving into this field and spent my life doing exploration. Now, by the way, this is actually the image of a rover that we have on Mars. It's a selfie taken by a rover, which is on the planet Mars. So this is a real picture. This is not, done in a computer lab. So people usually ask me, why do we explore? Why are we spending money to explore and push the field of science? So first, let me start telling you a little bit, one illustration of why do we do exploration. So if you look in a sky with a big telescope, this area of the sky corresponds to about, if you take 1/4, put it at the end of your hand, that's about the area of the sky that this picture is covering. And look how many thousands of galaxies you are seeing in that little area. So if you extrapolate to the whole sky, there are literally billions of galaxies in the sky. And probably you see it here, not maybe in downtown Riyadh, but if you go out to the desert, you'll see the beautiful sky, which is above you. And then if you zoom on one of these galaxies, you have literally, each galaxy is made of billions and billions of stars. Each one of these dots is a star, like our star, which is the sun. So when you think about it, there are literally billions of stars in our universe. And that's fascinating. And we believe that started 13 billion years ago, and there was a big bang, and a lot of particles were formed, and that led to the formation of these stars and these galaxies. And if you zoom on one of these bright areas, you see that star, which is the sun, actually has planets around it. So this is our solar system. You start with Mercury completely to the left, and Venus, then that beautiful blue dot, that's us. All of us sitting on this blue dot. Your friends, people you like, people you don't like, they are all living on that little dot that you have here. So that gives you a different perspective of our planet. Then you go to Mars, Jupiter, Saturn, and the other planet, Uranus and Neptune. And looking at our planet, there was on this little planet, there was the right chemistry, right temperature, right environment, that over billions of years, that led to the formation of cells, and then these cells created this beautiful world that we live in. So when you sit down and think about it, how did it start from the Big Bang, and it was only particle, and led to you and I sitting in this auditorium doing that? That's amazing when you think about it. It's amazing how did that happen? So one of the things we're trying to do in our exploration is to understand how did that happen? How did we start with the Big Bang? How did stars form? How did galaxies form? How did planets form? And at least on one of them, how did life evolve? And the next question immediately, is this common? Because we know almost at every star we look at, we find that there are planets around it. And some of these planets have similar environment to our planet. It has about the same temperature, same distance from the sun. I mean, we haven't gotten big images yet, but we see from the little dots, actually they have similar environment to our planet. So the next question, could have life evolved on them? And if life evolved on them, what's the nature of it? Is it similar or is it different? If it did not evolve, that would be equally amazing. Why did it evolve only on this planet that we're living on? So a key objective of our research is to basically figure out how did these things evolve and write what I call the book about how we came about. And of course, that's not going to happen in 1 year and one mission, but at least we can start gaining an understanding. So the first thing I'm going to, and I'll give you an illustration of what we are trying to do. So the first one I'm going to tell you about is exploration of Mars. And the reason Mars is of particular interest, the number one, it's fairly close to us. Mars and Venus are the two ones closest to us. It takes us only 6 to 9 months to get there. Now that might sound a lot for you, but if you were going to Saturn, it would take you 12 years. So Mars is fairly close, it's in our neighborhood. It has some similarity with Earth. It's about the size, it's 1/4 the area of Earth. So it's about the same area as the landmass of Earth. It has polar caps, like you see at the bottom here, which is made of ice and CO2 ice as an H2O ice. And it expands and shrinks depending on the season of the year, similar to what happened on Earth. The year on Mars is about 2 years on Earth. The day on Mars is about 24 hours and 40 minutes. So it's very similar to the day on Earth. Mars has an atmosphere, but it's much thinner than the Earth's atmosphere. It's about 1% the pressure that you have here on Earth. And for the geology on Mars, which will reflect on the evolution of it, it has a lot of similarity to the geology on Earth. This is the Grand Canyon in California. That's the Grand Canyon on Mars. So you see that the geology happened very similar. This is a surface picture on Mars and one surface picture on Earth. And here I give a test to my students at Caltech, and I'm going to give you a test. How many of you think the picture to the left is Earth? I mean, raise your hand. Okay. How many of you think the picture to the right is Earth? You know, it's interesting. I get the same statistics, you know, and I forgot which one is which. But to be more accurate, to tell you, this is Earth and that's Mars. And the point, the similarity between the two. The only reason I know this is Earth, you go back, you see a snake here? That's the only reason I know this is Earth. Otherwise, it looks very similar. You know, it looks very similar. So when one of you, the young people here, you travel to Mars, you're going to think you are landing in California, because that's where this picture, you know, was taken. So the point I want to make is that the geology on both planets is very similar. And to make a long story short, we believe that Mars was formed same time as Earth, about 3 billion years ago, or 3.7 billion years ago. At the beginning, Mars had, similar to Earth, had water on the surface. It has river on it because we actually see drainage channels, dry drainage channels on it. We see alluvial fans. If there are some of you are geologists, they are usually formed by liquid which erode, you know, the hills and create an alluvial fan in front of it. But we believe that then Mars cooled off much faster than Earth, and that water went and became frozen, you know, in the ground. So the key question is, could have life evolved in those early days, few billion years, you know, early days? And if it did, what does it look like? Where is it? So that's what we are trying to explore and find if Mars in the past was what we call a habitable, you know, environment. So now to tell you how we do this exploration, this is what we call the family portraits of the rovers we have on Mars since 2004. So for the last 17 years, we had continuous presence on another planet. And we had the rovers always operating, you know, and actually doing scientific investigation. So we started first by building this rover. So this was a technology experiment. We just wanted to see how do we actually drive on another planet. Because the challenge is different than when you have a little toy, you drive it here. It takes 10 minutes for the signal to get to Mars and 10 minutes to come back, you know, at the speed of light. So you cannot sit down and joystick it, because if you send a message and it takes 20 minutes for you to figure out what actually happened. So they have to have completely autonomous capability. That they should drive by themselves, avoid hazards, see what's in front of them. So we did that as a demo, and then we did 2 missions called Spirit and Opportunity, and that's these rovers here. They are about the size of your desk, and they are solar powered. Then in 2010, we sent a rover for Curiosity, this one, which is about the size of your car. And last February 18, we landed Perseverance, which is the latest rover that we landed on Mars. So as of now, both of these are still operating, you know, in different locations, you know, on Mars. Now, in addition to the engineering challenge that I will talk a little bit about in a minute, the other challenge is each one of these is like a chemistry lab, which is all incorporated into these rovers. So you could imagine if you go to one of your chemistry labs here, and how do you miniaturize that and put it on these rovers? So it has gamma ray instrument, X-ray instrument, mass spectrometer, has oven in it that we take samples, put them in the oven, heated to see what gas is being emitted, because we're trying to understand what's the composition of the surface, the rocks and the soil on the surface. So that's one of the biggest challenges. So we had to miniaturize everything, and these rovers run on 140 watts. So that's one bulb up here. That's the total power that we have. And we have to run the whole rover, drive it, communicate with it, use the instrument, do all the operation with about 140 watts. And they have, in order to collect the sample, they have arms, which is over in here, exactly similar to your arms, the same hinges. So we'll be able, and it has a drill at the end of it, so we can go drill in the soil, and it has a scoop, so we can take the soil, move it, and put it inside. You can see one of the covers here. We open it and put things inside that oven and do the analysis of it. So now let me tell you a little bit about the challenge, some of the challenges on getting there. When we send these spacecraft, Mars is about 225 million kilometers away from it. So after all that trip over 9 months, we have to hit Mars within 2 kilometer circle, to be able to land at the right place. To give you an idea how challenging that, I'm sure some of the engineers here already are doing the calculations. So it's the same as if I go out of my office in Los Angeles and hit a golf ball toward England, St. Andrews in England, where there is a famous golf course, that ball had to go straight in the cup. That's about the accuracy of this which we have to do. And if some of you are good golfers, the cup is moving at very high speed. It's moving at about 60,000 miles per hour, and you still have to get in that cup. So we have to develop a lot of techniques of navigation because we don't have a GPS network, on Mars. So we have to do different kind of navigation, both radio and optical, to be able to navigate that spacecraft and get it at the right location. The other challenge, you are all probably took a class of science. So if you look at the energy with which that capsule is hitting the atmosphere, to take 1/2 mass multiplied by velocity squared, that energy is the equivalent of 18,000 race cars going at full speed. And we have only 7 minutes from the top of the atmosphere to the surface to slow ourselves down and land softly on the surface so we don't damage, the rover. So basically we use a series of techniques. One, we use heat shields. So when we slam in the atmosphere, it's like when you're driving, you put your hand out of the window and you feel the pressure, except you are coming at much higher speed. And that heat shield has to sustain 2,000 degrees centigrade. That's how much the heat, to slow us down. So a lot of material science goes into developing that. Then after we slow us down a little bit, then we have to open a supersonic parachute, the biggest parachute ever opened, to slow us even further down. Because Mars' atmosphere is very thin, so it's not like on Earth where the parachute takes you all the way down. So that slows us some more. Then we have to fire retro rockets, to slow us even more, and then to hover over the surface. And when we are about 10, 15 meters above the surface, we use a sky crane to get the rover on a road down to the surface very gently. So you'll be seeing that in a video that I'll show in a minute. And just imagine all of this has to be done autonomously. So it has to be all intelligent, doing the measurement, figuring out where the spacecraft is. And we have to land in a very specific spot. So we have to move as we're coming in to home in on that spot. So that's what makes it, the engineering challenge that we have to face. So let me show you a couple of pictures and I'll show you the video of how that all is being done. This is the actual rover. This is the one on Mars, that's in the chamber at JPL as we are building it. You see people all wearing these suits because we want to make sure it stays very clean. Because one of the key things we want to make sure, as I'll tell you in a minute, we're looking for potential life on Mars. We don't want to take bugs from Earth and say, hey, we discovered life and it turned out we brought it with us. So we have to clean the rovers, keep them very clean. We put them in ovens, heat them, we clean them chemically. As they are being assembled, people are always very careful on doing the assembly. And now what I'm going to show, how do we actually package them? Because you'll be showing the video, and that will give you an idea. So we take that rover and we have to fold it in because you don't take a big rover, put it on the top of a rocket, there is no room. for it. So we actually fold the wheels, we fold all the arms, everything, so it's kind of flat in the middle here. Then we put it under what we call the descent model, that's the retro rocket, which I'm going to bring it down. Then we put both of them inside both the heat shield, which is in the front, and the back shell in the back, and then they get attached to what we call the carrier, that's a spacecraft which will take them to Mars and drop them in the atmosphere on Mars. So notice where you see where it says cameras. So we have a camera at the top, which will be looking up to take a picture of the parachute that you'll be seeing, or video. Then you have on the descent stage, you have a camera looking down, so you can see the heat shield, being dropped away. And then you have camera on the rover looking up toward the retro rockets, so you'll see how it's bringing it down, and a camera looking down to see the rover kind of being descended on the surface. So what I'm going to do now, and that's a big assembly room where we're assembling, all this hardware. So I'm going to take you to the mission operation room at JPL, where we monitor all our spacecraft across the solar system, and show you what was happening at the time when we were landing, on Mars. So there's going to be a video, and it has sound in it, so I'll kind of give you a couple of notes, but pay attention to what's being forwarded.
We are starting the Internet and Foreign Rights Neighbor, where the spacecraft will descend the entry down chapter in preparation for parachute deploy and roll over to give the radar that will open the ground.
So here you see the parachute open. So this is actually on Mars. So what you see behind you is the sky, on Mars.
And we're seeing acceleration in the velocity. Our current velocity is 450 meters per second, and altitude is about.
And now that's a camera looking down, and you see the heat shield separating, and you see Mars in the background. So this is like you are sitting on the rover, and you are looking down at Mars under you. And all of this is in real time. So I'm not speeding up or slowing it down. So if you were on the rover, that's what you'll be seeing. And you see the heat shield in the horizon dropping down faster. Mars is pretty dry now, so it's a little bit like Saudi Arabia. So it's like you are landing at somewhere in the desert in Saudi Arabia. And you see it oscillating a little bit because it's at the bottom of the parachute as we're coming down. And then we are looking we know where we want to land. So the camera autonomously is looking around to see where that location is. So it can move the spacecraft to home in, on that point. You see a lot of sand dunes on Mars. So that's an indication that water had eroded the rocks and created those sand dunes as you have the wind, blowing them.
The combination of organizations has produced a balanced solution in part of trail navigation.
And there is a radar instrument which measures the altitude and feed that information to the different activities which have to be taken place. And again, all of this is being done autonomously because you cannot joystick it.
We are currently performing the direct meter. Her velocity is about 75 meters per second and an altitude of about a kilometer off Mars. We have turning off the navigation. Current speed is about.
And then we drop and start using the retro rocket, and you'll see the plume of the retro rocket blowing up sand on the surface. So now we're getting really close. And then we're hovering now, and you are going to see on the top right, it's a camera looking up. So that's the hoverer, which is holding it. And on the bottom is the rover, and it's sky craning it down slowly to the surface. Then as soon as it touches the surface, we feel that. And then we cut the cord, between the two. And that one goes away. And you can see the reaction, of the people in the mission operation room. I mean, it is an amazing and very exciting time because this team have been working on this for like 10 years. And one thing which goes wrong, everything is is lost on doing that. So you can see the tension and the excitement. The other thing I like always to point out, you can see women and men in that room, and most of them are not much older than the young people who are here. So they are typically in their 20s and 30s. We have few older people like me who have a little bit more experience to make sure we don't mess up something. But it's really a lot of the young people who are really pushing the limit and making these kind of things happen. Now, the first thing we do when we land is we immediately take pictures to see, is everything fine? You know, did the rover land properly? You know, what's the scene around it? And you can see the shadow of the wheel in here, because this camera, I mean, we have like 16 cameras on it. This camera is under the rover, and that's the first one we take a picture of. Then over a period of couple of weeks, we sit down and test a different subsystem. So we are testing here the wheels, that everything is, you know, that the gears are working and everything is working fine. Then we tested the arm. So this is the arm, as you can see, the joints in here. So we're testing it that it's working. And what we are trying to do in this mission, in comparison to the previous mission we had, was to drive around and do in situ analysis. What we are going to do, what we are doing in this mission is over a period of 2 years, we want to drive around, look at what is interesting rocks, which potentially could give us insight into the environment, and drill in them and collect a series of samples. So you can see that sample like on the left is about the size of my finger. Then we have to put them in the sample tube and seal it to make sure when we bring it back to Earth, it's not going to get contaminated. Then we put the tube in this container, and we're planning to collect about 31 samples from a region of about 20 to 30 kilometers area. It's very close to an alluvial plain. And then put that container in one location. Then in 2026, we're going to send another spacecraft, which will land close to that container, grab it, and that spacecraft will have a little rocket on it. So we'll put the container in the nose of the rocket, lift it up, launch it, put it in orbit around Mars, send another spacecraft to rendezvous with it and bring it back to Earth. Just an interesting engineering challenge, you know, to do all of that. And the purpose is at the end is we want to analyze those samples in labs here on Earth, which are usually more sophisticated than what we can put on these rovers. And that those samples, pieces of them, will be distributed worldwide following a certain protocol. So we get the best minds to actually analyze and understand, you know, what's happening on Mars. And some of them will preserve them for the next 10, 15, 20 years, because there are always new techniques which will be coming out on doing analysis. So we want to make sure we capitalize on that. So that's the key purpose of that. And this is an example of the scene, you know, on Mars. As I told you, I could have told you it's Earth, and you would have believed me in some areas. Now, one thing people always ask me, some of you might have noticed, you know, that parachute had different pattern on it. So basically, the engineers, you know, at JPL, in addition to being smart, they have a good sense of humor. So what that code on the outside is the longitude and latitude of JPL. So if a Martian picks that parachute, they know exactly where it came from, you know, on Earth. So that's kind of one of the humorous things that engineers do. Now, one thing we added to this mission, if you recall when I showed you the rover, we started with a little teeny rover so we can learn how to rove, and that led to the bigger and bigger rover. So we put on this one a helicopter. Now, many of you say, what's the big deal? I have a drone at home, you know, what's the big deal here? Well, the big deal is, you remember I told you Mars is 1% the pressure, you know, on Earth? So this is like flying at an altitude of 30,000 meters. You have to go up 30,000 meters to be at 1% the pressure. Well, nobody has ever flown at that altitude, flown a helicopter. The record is at 12,000 meters. Mount Everest is 8,000 meters. So it was a huge challenge of developing the capability to get that helicopter to fly at that altitude. So what we had to do, the whole helicopter, this is a real helicopter, I mean, what is flying now. So the whole helicopter weighs 1.5 kilograms. And that includes everything. It includes the communication, it includes the scientific instrument, it includes the camera, it includes intelligence. So the helicopter, as it's flying, it has to decide where to land, so it doesn't land on a rock and then it will flip. And all of that has to be done autonomously, and it the power, you see at the top is a solar cell, so we can get the power to put it in it. So it was a big challenge. And these blades had to spin, I don't remember now, but like 60,000 rotations per minute to have enough lift to lift it. And here you see in the chamber where we put it to demonstrate that actually it would work. So we emptied the chamber, put only 1% pressure in it, and we put carbon dioxide because that's the atmosphere on Mars, because the interaction is different than here on Earth. And to show you that ultimately it worked. So here is a little helicopter being taken, picture taken from the rover. And this was our first test. So this is the first time ever humanity have a helicopter flying on another planet. So this was 113 years after the Wright brothers did the first flight, on Earth. Now we can say we have done the first flight, on Mars. And basically this is now is a demo, like that little teeny rover I showed you earlier. So we're already starting to look at bigger helicopters. And the advantage of helicopters is you can go and survey ahead of like a scout ahead of the rover to tell it where it goes. You can send it to high-risk area like those canyon I showed you earlier, or we cannot send a rover. So the geologists want to see what's in that canyon, so we can send a helicopter. So basically, it will allow you to go to a very high-risk area, which normally are more interesting, than and you see it coming down. And the intent when we build it is just to do 5 flights to demonstrate the technology. Well, we are now at our flight number 16, and it's still working, and it's being used as a scout to tell the rover where to go, where are interesting areas to go. And you can see an example of that picture taken from the helicopter. That's a shadow of the helicopter at the bottom, and you can see the tracks, of the rover, and then this is a picture of the rover actually taken from the helicopter. So the rover is taking a picture of the helicopter, and the helicopter is taking a picture at the rover. And when you think about it, this is happening on another planet. So when you think about it, it's kind of amazing. I remember when we did the landing, not this one, but the previous landing. After we did the landing, I walked outside the mission operation room. It turned out it was during the middle of the night. And it just happened that Mars was in the horizon. And I looked at it and said, we just landed on that little bright spot that is in there. So it's amazing what people, when they put their mind and work as a team, what can be accomplished. Now, let me tell you a little bit, so not everything is Mars, so I'll give you a very quick thing on what other things we are doing. This is a mission which is in orbit around Jupiter. And what we're trying to do is to understand the dynamic of how the atmosphere of Jupiter, I don't have it as a video, whereas Nora, next time we have to put a video, here. So this is a great red spot. It's the size of Earth, but you can take Earth and put it inside this red spot. It's a huge hurricane which is happening, and you have the dynamic, of all of these things. So we're sitting down observing them so we can understand the dynamic of the atmosphere on Jupiter, which could shed light on about how hurricanes on Earth actually form and actually evolve and what's driving them. One thing which is interesting around Jupiter, you see that bright spot to the left? That's a satellite called Europa, or a moon called Europa. It's about the size of our moon, a little bit bigger. But what's interesting about it, it's all made of ice, H2O ice, like what you have in your, in your cup. And you see these brown areas that are made of organic material, and you see these fractures on it. So we were baffled that, what is that? So we took higher resolution. And you can see on the top, I could have told you, I took that picture when I was flying over the North Pole. You see these ice flows, in the North Pole, so it was very much similar to it. And you see that they are being fractured, because you can look at some patterns and you see them suddenly displaced. That means those flows are moving. So that's an indication, most likely, that there is an ocean below that ice. I'm considering it's made of H2O, then that ocean, would be liquid. And based on this observation, magnetic field measurement, and gravity measurement, we believe there is an ocean which is about 4 times more water than on our planet. As soon as you say there is an ocean, immediately the biologist would say, could life evolve in that ocean? Like what happened on our ocean? Because it's H2O, there is organic material, and there is heat, because that's why it's liquid. in that. So that what one of the mission we're planning that I will be launching it in 2 years from now is to actually put a spacecraft which goes over Europa and use a radar to sound the ice, determine how thick the ice is, and find where the area's ice is the thinnest. And then in the future, we're planning to put a lander, drill our ways through the ice, and put a submarine, in that ocean and analyze the composition of that ocean. And in preparation for that, we actually built a submarine. In actuality, it's an upside down rover. And this is in a lake in Alaska where the surface is frozen. We drilled a hole, put that rover under it, and it's exploring the lake, driving upside down, exploring the lake. Being monitored from JPL from about 7,000 miles away, from it. It might look different, what we do on Europa, but that demonstrates the technology and the capability of being able to do that. So you could see something like this maybe about 10 years from now, or 15 years from now. Now, let me bring you back to our own planet to tell you, what we are doing, to better understand and hopefully improve the environment on our planet. First thing I want to watch you is you hear about ocean rise. Well, ocean rise is actually happening, and this is a demonstration of it. So we have been monitoring the topography of the ocean, or the average relative to the geo, and it's going up at the rate of about a few millimeters per year. Now, it doesn't take you long, in this case, it's 2 decades, and the ocean has risen about 1 meter. If we go for another couple of decades, large part of the earth will be flooded, coastal region. And there are literally 2 to 3 billion people are living in cities which are less than a couple of meters above the ocean, right? That's why you hear a lot in the Glasgow meeting recently, the big concern about what's happening with the ocean rising. Now you say, what's causing that? Well, we found out that there are 2 factors which cause it, both driven by the change in temperature. Number one, as we get more greenhouse gas in the atmosphere, it warms up a little bit, and the ocean gets warmer and the water will expand. It's simple physics from thermodynamics that if you heat it, it will expand a little bit. That accounts for half that rise. The other half is that the ice in Greenland and in Antarctica is melting. And we have been monitoring it from space with a mission called the GRACE. And look at the top right picture. We are actually on the average losing about 400 gigatons of ice every year. So if you take that ice and say the water, it melts, it goes in the ocean, that accounts for the other half. But the 2 of them are driven by the change in the temperature on our planet. That's why there is a big push of keeping things below the 1.5 degrees or no more than 1.5 degrees. That's one of the factors. There are other reasons, for doing that. So clearly, our planet is changing. And if we want to protect our planet for our kids and grandkids, we need to do something about the change in temperature, which is driven a lot by carbon dioxide and methane and what we're putting in the atmosphere. Now, one thing I want to mention to you is a mission which is going to revolutionize how we're going to be doing observation of our planet, which will be launched in 2 years. And it's a radar instrument which generate images very similar to black and white photography. I will show you, or sorry, even color photography if we have multiple frequencies. And this mission will be able to map the whole planet every 10 days and will be able to measure changes down to a centimeter, which are happening on our planet. And I'll show you why is that important. And that's at the heart of our collaboration with the King Abdulaziz City of Science and Technology here. That's the reason I regularly come here. So what that mission will do, because it uses microwave, we can see through the cloud. So it doesn't matter if it's cloudy or not. If there is dust, we'll be able to map the surface. And because it's a radar, that means we generate our own signals, so we don't depend on the sun like photography does. So we'll be able to image all the time, continuously, every 10 days, map the kingdom, and be able to measure the changes that are happening on it. And the example of images is what you see at the top left. It looks like I could have told you that they colored photography, and you would have believed me, but that's a radar image. It's the river and all the cultivation field. And the trick we use is if you take a picture now and you take another picture, let's say 10 days later, and combine them, it will work very much like interferometry or Fresnel fringes. If you took, I can see some people shaking their heads, so they know what these are, and that allows us to measure surface change to a fraction of a wavelength. In this case, the wavelength is 25 centimeters, so we can measure phase difference down to about 1 to 2 centimeters. And that's how we can measure the change on the surface. And let me give you a couple of examples. This is a picture which was taken, one picture was taken before an earthquake happened, and one picture was taken after the earthquake happened. And when we combined them, we were able to measure the changes. So if you go from a blue to another blue, that means the surface moved 1 centimeter. Now, the benefit of this is, say, what can we use this for? Well, where you see a lot of fringes, that means there was a lot of motion. That means that's most likely where most of the damage happened from the earthquake. That's where the rescuers have to go first. So we usually distribute this kind of data very quickly to the rescuer to do it. The other benefit is also, particularly in our case in California, where we have lots of faults and tectonics, as surface moves, around the plate, it bends a little bit, so you can tell which area are high risk that a break could happen, an earthquake could happen. And earlier today, I was with my friend Samer here at Cassie. He was showing me where are a lot of the earthquakes which could happen in the kingdom. But here you don't have as many. But if you go to the west side of the kingdom, you have the Red Sea fault, that's how the Red Sea was formed. And along that coast, there is a significant risk of actually motion and earthquake. And it's not something to be worried about, but it's to manage. I mean, in Los Angeles, we have plenty of faults in Los Angeles, and that, as we understand them, that led us to have a requirement on how you build buildings. So when an earthquake happened, the building doesn't collapse, but the building actually moves, with the earthquake. So it has direct implication of how you design, building, particularly tall buildings, if you understand what is the risk of potentially earthquake happening. And that's the example, as I was mentioning to you, along the west side, of the kingdom, and that's a research topic that our colleagues, Tamer, who's sitting here in the front, has been doing on understanding the motion which is happening, in the kingdom using this technique. So in 2 years from now, he's going to be getting images of the whole kingdom every 2 weeks or every 10 days. So it's going to be a challenge to see what's happening across the whole kingdom. Now, another application, this is Los Angeles. And we took this picture over a period of 6 years and look at the change, how Los Angeles is moving up and down. Now we say, how did that happen? Well, as we're pumping water from the aquifer, the surface subsides a little bit. And as the snow melts in the mountain, it comes and fills the aquifer, so it rises back a little bit. So what this mission will allow us to do is to look at the whole kingdom and see how much water is being pumped, and that will allow you to manage better your water resources. This technique is now being used more commonly in California to manage of how do you manage how much the farmers are actually pumping water and plan about the dams and all of the things related to the water resources. And in the Middle East, we have an even bigger issue, because here you don't get as much snow to fill it back up. And if you pump too much of it, you can have a major problem in the long term. And the other example, which is interesting for geologists, but also for archaeologists, you see at the top is a picture taken with a camera of the Nile in the region in the southern part of the Nile. And at the bottom is taken with a radar. And you can see what looks like a drainage here, which you don't see up there. So that shows where the Nile used to be many thousand years ago. And then that area got covered with sand, so the channel was buried, and the Nile changed its course. So we are going to be mapping the whole region of North Africa, the kingdom, or the desert areas. So the archaeologists are getting interested because they say, wow, maybe there was habitation in the old days along where these drainage were, because that's where most of the cities are built. So the archaeologists now are getting interested in this kind of thing. And these are the projects that we're doing now here, not too far from you, with the Abdulaziz City of Science and Technology. So we're going to be able to basically measure all the changes which are happening in the kingdom. Then we're going to be doing assessment of the water resources Another example, I didn't have illustration here about the sand dunes, about their motion, because those can have many implications, not only for the infrastructure, but if you are going to putting, we were talking earlier, doing solar cells or deployed across the kingdom, you want to make sure you are not in a place where you can get sandstorm all the time and then you have to go and clean them every other week. So there are regions that we can monitor over a long time of where are the best places to place that. And then the most critical part at the end is to take that data and visualize it so you can make people who are not like you, who are engineers or scientists, be able to understand it. Because they are the people who are going to make decisions, policy decisions in ministries and companies. And Kevin here is our expert in visualization, and here he's showing it, or the group was showing it to the Crown Prince, putting the data on a globe, so you can see it on a globe like Earth. And earlier, Kevin was showing, you actually can, there is an app, you can get it on your iPhone in Arabic, where you can get every day all the satellites that we have from NASA, the data coming from those satellites. So when we see carbon dioxide, carbon monoxide, the temperature, all of it, you can see it on your app. And that will be released, I think, publicly in 2 weeks. We have been working with our colleagues at TAC to do that. And as I told you earlier, it's a lot of fun to do that. Here I'm an engineer, and here I'm in the field working, with the geology. So I did a lot of exploration in Northern Africa, in not too far from here, in empty water on the Omani side. And I can tell you, it's a lot of fun, being an engineer, working and camping and doing this kind of work. And you get to meet a lot of famous people. How many of you have seen The Martian, the movie The Martian? Oh, okay. So you remember those two people at the bottom, Matt Damon and Jessica Chastain. So they came and spent a couple of days, at GPL to see how are we operating the Mars rover so they can apply it in what they are seeing in the movie. And I always like to end with this statement. And this is a quote, a piece of a quote from Teddy Roosevelt, who was the president of the US. And I hope you will follow it. And let me tell you the whole quote. The whole quote says, it's far better to dare mighty things, even checkered with failure, than to sit in the twilight that knows neither victory nor defeat. What that means, for people is, as explorer and as educated people, that you will be the leaders of the kingdom. You want to push the limit. You want to invent new things. And you should keep pushing the limit. So whenever the rule at JPL, we sit down and think about something which is impossible and then go and do it. And we know that we might not succeed all the time. We might fail many times, but that's how you learn. From doing it, from failures, you learn how to do things better the next time. One thing I tell my two daughters when they were in college, don't go and take the easy courses, even that you get an A. It's better to take the tough class and get a B, because you learn more from the tough class than from the easy class. So the key message to all of you, make sure you dare mighty things, both in your education as well as in your career. Thank you very much. It's a pleasure to be here. And if we have time, I'll be glad to answer questions. You hear me?
Thank you very much, Professor Rachi, for this very nice presentation and nice talk. It's full of information. And personally, I have most of my students here. I teach them satellite communications, I teach them radar, communication system, 2 people, whatever. Raise your hands, so we have all of these are engineering students. Okay, information coding and theory, most of them again. Now we have also preparatory school, preparatory mathematics students. Okay, so for those of you, I just want to let you know that before I come to the lectures, I watch YouTube videos and I come across videos on YouTube of you presenting these kind of things and see the people with this expertise. So I just want to tell the people how much important was this talk. Okay, so I learned myself from this knowledge, from this expertise, and I come and teach it. So it was very interesting talk. Because I have the mic, okay, I will start with one question. Okay, so you showed yourself as an engineer in 1981, I personally saw a video of you in 1984 explaining how the shuttle communicator is going to work and stuff like that. I believe that the challenges that were there at that time, it what drove the technology, right? And produced the consumer electronics that we have in our pockets nowadays. Is that true?
Yeah.
Yeah. So is it the case right now? Is it still the space research driving the consumer electronics, or now the situation is different? It's the consumer electronics driving the research. Not they rely on off-the-shelf components and stuff like that. Still have the money.
Yeah. But let me mention one thing when it comes related to what you said. I was a young student like you. I had no idea that I was going to be heading the most important NASA lab in the United States. But I was excited about science. I was adventurous. I did all kinds of things, and that's what I am. Now, you don't have to all of you go to the United States to do that. The kingdom is starting a space commission. And there are programs. I mean, actually, space are being built by actually, you can participate, in the whole field of space, exploration. And but sometimes people ask me other than the benefit. I mean, I described to you that that's an intellectual benefit. But there are lots of practical benefits which come from space. I'm sure you probably realize it, but most of the people don't realize that when you locate yourself with your iPhone, you have a GPS satellite. If you didn't have those satellites, you wouldn't be able to get the accurate and the Google map that you get. When you look at the weather report, that's all taken from satellite. And people think that it's coming from somewhere. I remember I was once giving a hearing in Congress in the United States, and one of these congressmen, and that's supposedly a smart person, said, "Why do I need weather satellite? If I want to know the weather, I can turn the weather channel." I told Mr. Congressman, we forgot that this is coming from a satellite. I had to do it nicely, to tell him. The other example I sometimes give, all of you have cameras in your iPhone. You never buy an iPhone without a camera. The focal plane in that camera is technology which was developed at JPL for our telescope, many years ago. Because we wanted to have a focal plane with CCD, which are very lightweight, very low power. We didn't think of the iPhone, but some entrepreneurs thought, wow, I can use that technology and have it right. So these are examples of the benefit of space that sometimes people don't think about it, but really could make a major impact on our life, and I can give you lots of examples. And I'd be glad to answer the question or to hang around in case people want to know.
Okay, you have a question? Yes?
Yeah, now take it easy on me. He told me to prepare a question. Don't ask the really tough question. Can you speak a little louder?
Technologies available that we're using to explore space. For example, the Planetary in Turkey. Do you think that those technologies could be used to explore other spaces in South America, in Russia, the new caves found in Scandinavia, showing that our previous knowledge of civilization, which we thought existed in Egypt about 3, 4, 5,000 years ago, is wrong, and the Planetary dates back to 12,000 years ago. Do you think we should focus our resources on stuff like that, other than exploring the unknown?
Yeah. That's a very good question. Now, in general, in the US, what we are doing there, we are developing the technology for our mission. But then we make that technology available to everyone. Everything we do at NASA is public domain. And then we are hoping that entrepreneurs will take those ideas or research it and then make them apply. So I gave you the example of the iPhone. I wish I knew we can use it on an iPhone. I would have bought stocks in that company. So our purpose is really developing technology to be able to do our mission and gain knowledge. But that's how things happen. You don't sit down and say, well, let's see, I want to develop something for a purpose. Sometimes it happens. But sometimes you develop something just because you are curious and you find one sudden application for it. And a lot of things happen that way. In fact, it happened more that way than saying, oh, I want to build an iPhone 20 years ago. So again, the benefit of a university, why it's important to do research, is you would do research for the fun of gaining knowledge. And then hopefully people will pick that up, or you would take it and start a new company and make it, apply. So purpose of just knowledge is very important.
Thank you for the presentation.
If you take your mic, I can hear you better.
Thank you for the presentation. When we human beings arrive in Mars,
What is what?
when we human beings arrive in Mars,
Humans.
Oh, sorry. Okay, I should have guessed that because I always get asked that question. Let me put it, today we have most of the technology to send the human to Mars. So that movie, The Martian, is not too much science fiction, but it has challenges in it. It's not as straightforward. Because number one, if you are sending, let's say, 4 or 5 people, so you have to take on your food. It takes 6 months to 9 months to get to Mars. You have to stay on Mars for 6 to 9 months, come back. So you have to take your food, your water, everything you want to take, to survive. You have to take it with you. And also there is a psychological impact. I mean, if you are sitting in the little capsule with 6 of your best friends, I'm not sure they stay your best friend by the time, 9 months from now. But so there are, and this is serious, I'm not doing it as a joke, there is a psychological impact, sitting in a little cabin or rooms. So one of the solutions to address some of these is to do what we call live on the land. So we are developing technologies where we actually see in an enclosure, like in the Martians. If we can find water, be able to pump water, so we don't have to take it with us. Water will be used for agriculture, so we can grow our food, the astronaut grows their food. Then water could be split into hydrogen and oxygen, so you can use oxygen to breathe. And then you can use both oxygen and hydrogen to bring the rocket back, so we don't have to take all our fuels. So the approach to it is to figure out the technology and the capability that we can generate what we need on Mars. So we have to take only the 6 months that we are going there. So it will be a challenge because we have to do the habitat ahead of time. We have to deploy maybe solar cells or maybe nuclear to generate, the energy and the electricity to do that. But I would say that could be possible within the next 15, 20 years. So during the lifetime of many of the people sitting here, it is possible to actually go to Mars. Now, I want to be kind of more clear. When people talk about building cities on Mars in the next 20 years, that's a stretch for us to do that. So probably start in small steps before you get to the large scale.
I didn't have a question, but I saw a picture with Jacques Cousteau, and then Jacques Cousteau is the discovery of this ocean. And they said, just my idea is another perspective of exploring Mars. So it is known that the water in the Earth is more than 70% of the surface. So why we don't have exploring the life in ocean and water underwater, which represents 70% is very close and need less technology, and the water is already there. I think the life is already there. And then we expand our surface rather than exploring all, which is scientifically sound, of course. This is just maybe a question.
You mean exploring our ocean?
Yeah, exactly.
No, I mean, that's a very good question. Because sometimes people ask, we know more about Mars than we know at the bottom of the ocean. And that's a very good question, but both of them need to be done. So usually our thinking is you don't do A and not do B. I mean, if you want to gain knowledge, there are exciting issues all across the board. A number of those technologies, in fact, this radar and so on, we cannot use radar for mapping the bottom of the ocean. We can use sonars, but the technique is very similar to the technique that we are using. So there are a lot of activity now about exploration of the ocean bottom. That submarine that I showed you. In fact, when a number of explorers were going to map the bottom of the ocean, they came to JPL for us to tell them what we're doing in robotic autonomous vehicles, because we developed those like 20 years ago. So a lot of the technology is also applicable, and people are exploring, the ocean here on Earth and understanding that.
You want to take a question?
Sure.
I want to ask about the moon, why aren't we now on the moon?
heard about it. And the second is, repeat the same question you started with. What is the main reason of discovering? Are we looking for real life there? Other people?
Okay, we about life in the universe and what we do about it if we discover. People are always asking the question, do I believe there is life in the universe? And I say absolutely, but I cannot demonstrate for it. And being a scientist, you always want to demonstrate. You know, when you make a statement, you want to demonstrate. And the reason I think life would exist across the universe is number one, we do see there are planets. You know, almost every star we look at, we see there are planets, you know, around it. We know a lot of chemistry and physics and biology are the same everywhere in the universe. So it's very likely that life could have evolved. There is no reason why it evolved on this spot. You know, now, would that life be similar or would be different? We don't know. And that's one of the exciting things that we are looking at. And the benefit of trying to find it is, would it look like us? And it doesn't mean like us, human with two eyes and two ears. Is it based on DNA? Is it based on carbon DNA? Or is it based on something different? You know, so I think it will shed a lot of light, you know, about, you know, how did we come about? How did we evolve and how did we come about? Now, if we discover how do we communicate with it or how do we, I don't believe in UFOs, or at least I'm skeptical about it. So if we find planets which are similar to our planet, most likely then we need a lot of telescopes to actually look at that planet, radio telescope, and see can we detect radio signal coming from it. Because the nearest star to us is 4 light years away. But the microwave or visible light takes 4 years to get here at the speed of light. So the likelihood of a spaceship is unlikely unless they are very, very advanced. But the radio signal will get there. So you'll be able to detect the radio signal and you'll be able to see has a certain pattern to it or is it natural? Because many stars in its natural, you know, microwave. So a number of people are looking at that, but you saw how big the sky is, you know, you cannot look at all of these, you know. So but if we find a planet that we see with telescope, which has the same temperature as our planet, looks like it has oceans or something similar, then most likely that's what we focus on. About the moon?
Yeah, why aren't we on the moon?
Our moon, you mean?
Yes.
But you mean like,
I mean, we focus more on Mars.
oh, I see. Why Mars, not the moon?
Yes.
Well, our moon is very, very dry. And we don't think that in the past it had water on it. We think the moon, as you see before, was all the craters that have been bombarded all the time. We don't think it ever had an atmosphere. When you look at some of the Mars images, I bet you I can show it to you, the rivers, and tell you that's in Saudi Arabia, you would believe. You know, or it's in California, and we do see vegetation. But we actually see, like in the dry desert, when we fly over it, we see all these drainage. That's exactly what we see on Mars. So there is a higher likelihood that life could have evolved.
Yeah, I see many hands, but so forgive me if I cannot come to all of you. Maybe a couple of more questions.
How do you study the samples that have been taken by Rovers? And this is able to break samples back, bring it to Earth? How do you study
I don't hear very well.
How do you study the samples that have been taken by Rovers? Is it
How
able
do
to
we
break the
establish-
samples down?
How do you study the sample?
How do you study?
Oh, the samples on the rover?
Yeah, how to make that.
We are not studying them on, well, let me answer it to start. On the previous rover, not the last one that we have now, but the one which is running. So we drill in the surface, we take the dust, put it inside an oven, heat the oven, and then see what's gas is being emitted from. And then we have mass spectrometers, which will tell you exactly what are the composition of that gas. That's the one which we launched 10 years ago. The new one, what we are doing more is to look at the rocks, and we have a number of instruments like a microscope, a gamma ray instrument, UV instrument, and we want to see which ones are interesting. And then you have a group of scientists who sit down and debate for weeks, like this is interesting or that is interesting. And then if there is a consensus, Then we go drilling that rock, with a drilling machine, like what we use at home, and pull that sample, and then we bring them back to us to study in your chemistry lab or the chemistry lab anyway. And it's interesting to see the debate between the scientists. We can collect only 31 samples. And you want to make sure, one, you pick the right ones. Number two, that there is a diversity of samples, because we don't understand exactly how life could have evolved or not. So we want to have a diversity. So there is a whole process, and there is a couple hundred scientists, geologists, who are involved in that, in completely feed geology. Because that's what normally they do when family goes and doing geologic mapping, they looks at the rock. Oh, this is interesting. I'm going to bring a piece of it to the lab. We're doing the same thing, except we're using a rover to do that for us.
Maybe one final question from this side.
If you come one day to the conclusion that there is definitely no life on any closed planet, how do you think that would affect the amount of funding to space agencies?
If we don't see any life on any planet, is that
if you are sure that there is no life on any closed planet?
That could happen. If we find that there is no life on any of these planets at all, then you wonder how did it get created here. Now, people always ask me, and I'm going to jump and answer the question. See, people ask me, what created it here? And then my answer is, God created the whole universe. God created these billions of stars. Why did he pick this planet to put life on it? God is so powerful, which I believe, I'm a religious person, but he would have put life on all of them. So anyway, that's kind of philosophical question that you can have.
My question is about the effect of that conclusion on the public funding.
On funding. Sorry, I thought we were talking about blood. No, in general, the funding is not driven by funding life. Even that's very important. Funding is driven for gaining knowledge. At least in the US, and I dealt a lot with people in Congress about the funding, they have to encourage them, about the funding. There is a strong interest in gaining knowledge because they believe that by gaining knowledge, we can gain technology and that will impact our economy. It's more driven, by the economic impact than finding life, at least in the mind of the funding, Now, as a scientist, we're curious about life, as an example. But in general, the funding for NASA has been fairly stable, even independent of the life issue. Now, if we find life, I'm sure there will be a lot of curiosity about really trying to understand, what does that mean? But now it's heavily driven about the economic impact, the excitement of young people. I was a young person when we landed, on the moon. For me, it was very exciting, that many people ended up being scientists and engineers in the US during that period because of the excitement. And they benefited across the world, not only in space, but across the world. So I think a key message here is we want the young people to be excited about what the country is doing. And that if it's something technological, then they will jump in technology. They don't end being all space engineers. They might end different kind of engineers, but you gain education, and that strengthens the economy of the country.
Okay, Dr. Rucci, we know that your time is precious, so thank you very, very much for this time. Please, if you will allow us, stay with us to take a picture with the CME and electrical engineering students and faculty with you. And then if you would allow for a couple of questions, the informal questions after. Okay. Thank you very much for coming. Thanks a lot.